Hi, everyone, and welcome to our webinar on the evolutionary differences between Cassandra and ScyllaDB. Today, let's discuss how both Cassandra and ScyllaDB evolved from their origins, what makes them different, how some features compared among both databases, as well as briefly touch on some different direction decisions that each database took over the years. So, my name is Felipe Mendes, and I work as a technical director here at ScyllaDB. I am also one of the co-authors for database performance at scale, and I often work closely with our users and customers on scaling their data-intensive applications. Along with me today, Guy will touch the second part of this presentation. So, hi, Guy. Why don't you
Hey
go ahead
everyone,
and introduce yourself? Yeah.
I'm Guilherme Nogueira. I'm a previously solutions architect at Scylla, technical director now, and I work with industries such as publishing, streaming, automotive as well. So 3 years of experience, and now bringing some of that knowledge through webinars for you.
Awesome. Thanks, Guy. And yeah, with that, guys, we have a lot of things to discuss today. So let's jump straight to it. Since today is pretty much a live presentation, we pretty much wanted to start with a poll asking how familiar and how experienced are you with ScyllaDB and Cassandra, because let us know how much you do know, because then we will basically shape the content of today to match your actual level of experience. All right? So let's get started with discussing Cassandra and ScyllaDB similarities and differences. So, starting with the similarities, it turns out that both databases actually share a lot in common in their fundamentals, though some design decisions are slightly different from one another. And we are going to be covering each of those design decisions as we move throughout our presentation today. For example, both Cassandra and ScyllaDB implement a distributed peer-to-peer architecture, where each node in your cluster can actively serve both read and write requests. In Cassandra, nodes are shared nothing entities, whereas in ScyllaDB, we make CPUs independent of each other. So that's a fundamental design choice difference among both databases. Uh, Both Cassandra and Scylla also shard your data automatically, while in Cassandra, each shard gets replicated to a node level. In ScyllaDB, actual individual CPU cores are shards of your data. And it happens that in ScyllaDB specifically, this combination of sharding data per CPU and managing it in a shared nothing manner is what we call in ScyllaDB as our shard per core architecture. That's one of the big differences when we talk about ScyllaDB and Cassandra compared. Both databases also support things like global replication. They also speak the same query language with some nuances here and there. And both also follow a wide column model for data distribution, where partitions, the way you come up with your data model, your partition key or your hash key determines the sharding of your data and the data placement across your cluster. And quite notably, all those similarities converge to both databases having a compatible ecosystem, where Cassandra users use the ScyllaDB Rust driver, for example, in case they're developing their application in Rust, without really any compatibility issues. And ScyllaDB users likewise can benefit from tools from within the Cassandra ecosystem. Both databases also apply similar anti-entropy mechanisms. So, what do I mean by anti-entropy? Things like hinted handoff, speculative hit rise, all kinds of repairs you are probably used to. Cassandra, for example, has the ability to run incremental repairs, and they are on their way to make repairs completely autonomous and transparent from the end user. Here at ScyllaDB, we are on our way to implement incremental repair and automatic repair as well. And lastly, but no less important, both databases also implement and follow a log-structured merge tree as their storage engine. And therefore, both databases have processes like compactions and so forth. So those things really exist across both databases. So as we go into the differences, uh, I'm going to talk about a few features that I hand selected here that I believe stand out. But note that this is not necessarily an exhaustive list. And Guy will later speak to some other interesting features in deeper detail. So things like vector search, which yes, we have vector search now, observability, and so on. So the first feature that I really handpicked, where I really want to talk about the differences, is really tablets. And the tablets happen to be a ScyllaDB exclusive feature geared towards elasticity and better resource utilization. And if you're coming from the Cassandra world and you are not familiar with the concept of tablets, tablets are just a small fragment of individual tables which can get load balanced across their cluster independently. And what tablets do in Scylla is they really evolve from Cassandra's static distribution. As you can see here on the left-hand side, where data of several tables really span your entire token ring or key space. In fact, if you wondered why we have to create a key space before you create a table, it's exactly because the key spaces span your token ring. Um, if we look into the right-hand side here, we can see that with tablets, data from each table gets split independently into smaller chunks, and the end result of this tablets-based architecture is that this brings elasticity to ScyllaDB. And Guilherme will later today show us an example on how ScyllaDB elasticity actually manifests in practice compared with Cassandra. Okay, let's move on to talk about Raft. Raft is a consensus protocol which brings strong consistency to ScyllaDB. And note that Raft is primarily used for managing metadata. Things like safe schema changes, uh, that when you create a cluster, you don't need to, manage your authentication key space or application factor manually, and also strongly consistent topology changes. Now, if you are familiar with Cassandra, then you probably know that some operations can be pretty much unsafe, like running concurrent schema changes may cause gossip to enter a state where it is unable to reconcile all changes you did, which effectively cause a production impact. Or you cannot run parallel topology operations like adding it or removing nodes because those could introduce data loss. And the Raft in ScyllaDB are really the way we came up to address those eventual consistency problems when managing the database. And Cassandra, they did acknowledge that problem already, and they are planning to address it with an upcoming feature that they called as transactional cluster metadata, or TCM. And in the future, we also plan to extend Raft to act on the data plane so that you could get strongly consistent queries, just like you have today using Paxos and lightweight transactions. Okay? So next, let's talk about workload prioritization. Workload prioritization is yet another unique feature in ScyllaDB which exploits our user space schedulers. And it allows users to assign different priorities on a per workload basis. And its idea is quite simple. It happens quite often that users have a need to run multiple workloads under the same data set. So for example, that's the example we often use, Chink running batch analytics and real-time workloads. And one of the things you typically don't want to happen is your batch workloads to impact the latency or performance of your real-time workloads. In the Cassandra world, which is demonstrated here on the left, uh, the only way you could actually isolate those two workloads altogether would be to, provision separate data centers, which ends up introducing consistency concerns and quite notably elevates infrastructure costs because now you have two regions instead of just one. ScyllaDB is actually workload prioritization is depicted here on the right-hand side, showing that the same workload can be run on top of the same group of nodes you already have. And what workload prioritization does is it will identify the queries you are running, and it will automatically prioritize that query in contrast to requests with a lower priority. And the end result is that when a separate workload is running, your latencies are actually, your most strict latency requirements are kept low without any impact. Okay? So let's now talk about another ScyllaDB unique feature, which is called, I particularly like it a lot, which is called repair-based node operations. And to understand what repair-based node operations are and which problem it solves, let's pay attention here to this diagram here at the right-hand side. So consider that you have an application writing to the cluster, and your writes, they will go to a coordinator node, and then they will get replicated to your replicas. Pretty much straightforward, right? And suppose that next one of the replicas fails to receive that write. And because two replicas actually acknowledge that write, that request, which failed to replicate to a single replica, is considered successful. So at this point, so far so good. However, later, at some point, you could end up in a situation where you lose one of your nodes, either because its disks got corrupted or because the hardware had to be retired. So at this point, after that sequence of events happen, we have a situation where one replica in your cluster is consistent, our coordinator node, which received the initial write. One is gone because we lost it, and the third one is inconsistent. So what you would typically do in that situation is, well, you would replace that replica with a new one, the failed replica with a new one. And when you run that process, it could happen that the previous stale token range, which previously failed to acknowledge your original write, strings data to the node that's joining. And the end result is that now a majority of your cluster has inconsistent data. It effectively turned it out into a majority. Now, this is something which, as you may guess, can be solved simply by running repair, right? And repair-based node operations in ScyllaDB effectively prevents this situation, which I just described, from ever happening in your cluster. Because every topology operation, like adding nodes, removing nodes, replacing nodes, or rebuilding nodes, use repair when transferring data. Therefore, after you carry out topology chains, ScyllaDB gives you the guarantee that your cluster is, your resulting node and your cluster is fully consistent. And to be quite honest, I am not aware of any equivalent feature in existing Cassandra today. Do let us know in case you have one. All right, so let's now talk about the features here at the bottom, starting with incremental compaction. Incremental compaction is ScyllaDB's way to provide a hybrid approach to compact your data. By hybrid, I mean not making it as aggressive as leveled compaction strategy, but also reducing the space amplification requirements involved with the traditional size tiered strategies. This means that with ScyllaDB, you can rest free from scaling out your cluster when your disk space utilization hits 50 to 70% utilization. And even with tablets, we can safely drive disk utilization up to 90% utilization. Cassandra recently introduced in their Cassandra 5 their unified compaction strategy, which is akin to incremental compaction strategy, but it's super new. I can't speak too much about it because I haven't run lots of tests on it. But the idea is quite the same. It's providing a hybrid strategy for the end user. Now let's talk about ScyllaDB's row cache. And you might say, wait, there's nothing different here. Cassandra also has its own cache implementation. And that's true, but Cassandra's row cache is only advised to be used in very specifically workload scenarios. And we are going to discuss shortly how it performs at scale. In contrast to Cassandra, where caching needs to be opted in, ScyllaDB implements its own caching layer in front of the database. It is enabled by default, and we even compared it against main cached last year, where we showed that we have quite comparable performance. So effectively, because of ScyllaDB's cache performance, many users, when they are moving from Cassandra or other databases to ScyllaDB, they find out that they can consolidate their existing caching infrastructure and their database as part of their migration, which provide even further cost reductions. Um, well, another exclusive feature of ScyllaDB is our DynamoDB compatible API, which we call ScyllaDB Alternator. And this is quite nice when you also want to consolidate workloads. For example, using workload prioritization, the workload prioritization feature I mentioned earlier. And ScyllaDB really allows you to run your DynamoDB workloads outside of the AWS ecosystem. The way it works is quite simple. Because the Dynamo and the Cassandra protocols are very similar, in fact, so ScyllaDB just reuses its existing architecture to support things like DynamoDB global tables or DynamoDB strings, and so forth. So yeah, Cassandra has, of course, no comparable feature, as their direction is really focused on the CQL protocol. Um, we then get to the last feature, which I brought for me at least to discuss today, which are guardrails. Like guardrails are really features to prevent users or administrators from doing wrong things in your existing clusters, right? And ScyllaDB per partition rate limits are really there to prevent high activity under specific keys, which could eventually become detrimental to latencies when your database is unable to keep up with bursts of requests. For example, um, many of our users have situations where bots could span their endpoints, and that would manifest into high database activity, whereas they would rather, just shed those excess requests so that they could keep the performance optimal for the majority of their users. Now, Cassandra also has a concept called guardrails, but I am not really aware of any related feature specific to keeping database latencies under control and shed access requests. So if you currently have a problem with bots spamming your database or something like that, per partition rate limiting is really an interesting a feature to take a look at. Okay. So these were just some of the features which make ScyllaDB and Cassandra different. And with that, I mean, before we discuss how performance compares, uh, do let us know how large are your existing clusters. And while you guys are answering, let's now shift our conversation to discuss some comparable performance numbers. So what we did was we've set up a three-node cluster for both Apache Cassandra 5.0 and ScyllaDB. We ingested over 1.5 billion partitions and then ran some performance tests. For Cassandra specifically, we used their Cassandra latest.yaml file to ensure that we were, benefiting from all of Cassandra 5 newer features, like Trie, Memtables, and SSTables, and so forth. And one of the aspects we realized when we started Audi's work was that Cassandra performance is highly dependent on the settings we've used to configure it. For example, in this chart shown here on the screen, we demonstrate a uniform workload showing how different settings to Apache Cassandra can significantly impact both throughput and latencies. So, as you can imagine, running out those tests alone can take quite a considerable amount of time. So one of the key lessons we learned while running those tests is that getting Cassandra to perform can become quite decently if you are not familiar with its internals. In contrast, ScyllaDB performance still managed to exceed Cassandra's 5.1, as we can see here on the blue line here on G chart. And Guy is going to talk later about how tuning ScyllaDB is pretty much easy to do. So after observing those results, what we did was we took a histogram from the best results of both databases and we compared them side by side. And one thing we noticed was that Apache Cassandra really implements that concept of thread pools for driving concurrency and parallelism high in Cassandra. So in Cassandra, we have a thread pool for requests, another one for processing writes, another for internode messaging, another one for reads, and so on and so forth. And Cassandra do allow us to tune those thread pools to improve performance, and we tried that, but we were not really able to drive throughput further or latency or get latencies lower from what we really observed. And because of this Cassandra design decision of using thread pools, what we observed when we look into the chart here in the bottom specifically is that both reads and writes really grow side by side. The latency of reads and writes really grow side by side as the database starts to become saturated, which is demonstrated here by those blue and red lines here. Compared with ScyllaDB, which are really the green and yellow lines, reads and writes distinctly report different tail latencies as the workload progresses. And this is a big win for ScyllaDB's architectural design decisions, as it shows how it prevents the added latency of just writes or just reads, for example, from affecting other types of queries. So let's now take a look into other workloads. Starting from a caching one. I previously mentioned that ScyllaDB and Cassandra took very different approaches related to caching. In Cassandra, you can use either the operating system page cache or you can enable their row cache. And we actually tested ScyllaDB against both setups in Cassandra 5, where from those results, we can see that no matter which distribution we look at, mixed, read mostly, or write mostly, ScyllaDB still drives at least twice as much traffic compared with Cassandra 5 under similar infrastructure. So quite notably, you may argue correctly that the previous workload we've shown aren't really realistic workloads, right? Because workloads in reality, they don't only use a cache, or they don't only use disks, which was the case for the uniform workload. So we really tested that, and we explicitly created a profile that would drive 20% requests only to disk, and the remaining 8% would read and write the very same data set over and over. And it's interesting when we try to stress the system as a whole, disks and memory and CPUs, as the results particularly reveals how ScyllaDB drives the hardware, both memory and storage utilization, to higher concurrency and performance compared versus Cassandra, which in turn is really how ScyllaDB helps with reducing infrastructure usage while sustaining higher throughput and even lower latencies. Okay? So all that said, I would like now to call Guy back because he's really going to drive us and talk more about how ScyllaDB and Cassandra are compared. Hey, Guy.
Amazing. Thank you, Felipe, and hey again, everyone. So here's another aspect that is not that often discussed. How long does it take for Cassandra and ScyllaDB to scale? Let's understand why does that effectively matter. So it's been, as Felipe said, quite some time that ScyllaDB shifted apart from Cassandra on how we fundamentally handle topology operations. Today, ScyllaDB fully decouples the topology changes from streaming or the process that moves data around your cluster. So even before we had tablets, every topology change was safe and guarantee that your data will be kept consistent thanks to that repair-based node operations technology we implemented. Today on ScyllaDB, bootstrapping new nodes is done instantaneously, whereas Cassandra, this is only accomplished after streaming completes. And this is a problem because not only is streaming Cassandra unsafe, as Felipe demonstrated, because it's streaming from a single replica, but it also means that you must carry out those operations serially and manually. So once you add a node, you wait for it to complete, and then you add a node, and then you wait again, and so on until you actually finish scaling your cluster entirely. And now imagine that you need to scale your database capacity because you've hit your existing limits. You're at the roof of your processing power. How can you wait hours or even days for a cluster to scale? That would for sure impact your business operations. Um, Here's another demonstration how the custom defaults can be very misleading. If you look at the bar chart on this slide, and you see that we got 3 different results for both bootstrapping and decommission node times. The first bar, the one in blue, shows that the operation took hours compared to the red and yellow bars. So you might be wondering what happened here. Well, it happens that if you go to the Cassandra documentation, they're basically saying if you want to benchmark their new zero copy streaming feature, you should set this option. Not only that, they basically changed the option name from Cassandra 4 or 4.0 for that matter, between 4.0, 4.1, and Cassandra 5. And do you know what's worse? Neither of those documentations actually work for you to tune that streaming speed for zero copy streaming. You have to go to Instacluster, which is a third-party service provider, to figure out what is the right option to use for that use case. In that case, it is a bit annoying that Cassandra defaults to throttling the overall streaming speed to only 20 megabytes per second. Again, this is a default, and that's how they intend the system to be used. But ScyllaDB does a much faster approach to this. After we managed to find the right and correct information option, a configuration option, those were the ones in the graph are the streaming times. Eliminating the longest runs, Cassandra claimed zero copy streaming should improve scaling by 5x or 5 times when they initially announced that feature, which is clearly misleading if you're giving those that we're seeing here between zero copy streaming and without that functionality. And by the way, in case you do not believe us, the link to the slides basically point to the Wayback Machine, so you can check the documentation, come up with your own conclusions about the Cassandra documentation by yourself. And here's another problem. When you scale Apache Cassandra, you need to clean up, which is you can't just decommission your nodes and forget to clean up, because otherwise you risk resurrecting your data. The thing about cleanup is that it's always a very redundant, time-consuming, and very resource-intensive process, which takes a long, considerable amount of time simply to remove data that's stale to that cluster. And the good news is that with tablets, we eliminated cleanup completely. In the meantime, Apache Cassandra takes somewhere between 50 minutes to 1 hour to clean up a single table in our tests here. And during that time, you can see on the right side that what happens to your latency during that operation. We particularly like to point out that the latencies over time, not only because it's very visual, but also tells a story. That you can see that at the beginning, there was basically nothing running. So when cleanup starts, and then you see a much more frequent spikes in user latency. That goes throughout the whole operation. And interestingly enough, if you look at the bottom chart, the one that has two green lines, you can see that one of our runs, we observed two very large stalls, which reduced our throughput considerably while the cleanup was running. So here's a comparison in time that it takes for you to double your cluster size from 3 to 6 nodes on ScyllaDB and Cassandra. It should take only 15 minutes on ScyllaDB, assuming the same data set that Felipe mentioned at the beginning. You add 3 nodes in parallel, they immediately join the cluster and then start to serving requests, and that grows as across time as tablets are streamed into that new joining node. 15 minutes, the time to take for streaming to fully complete the cluster is completely stable in terms of tablet movement. And in Apache Cassandra, it takes a much longer period of time. So the first node takes around 15 minutes to stream data, and only then there's a second node joining, which will also take 15 minutes, and so forth. We saw roughly triple our out of time, as well as the account for cleanup time, which is a much longer period while still serving traffic. And an interesting outcome we observed during our test is that after we scaled out our cluster back to, we scaled back into the original cluster size, we noticed that one of the Cassandra node that had been removed from the cluster was still left in gossip. So we noticed that because our loader's application started failing, and when we looked more carefully, we realized that we weren't able to perform schema changes any longer. There's absolutely no way we can actually benchmark this, but we noticed that after the cluster went back to normal, after a simple rolling restart, so that fixed it. But those types of shortcomings and inconsistency are something that ScyllaDB addressed a long time ago with Raft for consistent schema changes, and Cassandra clearly still suffers from it. So as we're still talking about scaling, let's jump into a quick demo on how scaling works on ScyllaDB xCloud. Oops. So this is the ScyllaDB cloud panel. Here I have a cluster that was deployed using just 3 nodes of I4I2X large. I'm connected to this cluster, sorry, via VPC peering, and I'm issuing requests according to the cluster size. So let's leverage the Scylla xCloud scaling policy by clicking on the Edit button. And then we see 3 different ways of scaling a cluster, triggering an immediate scaling out. First, there's the instance family of choice, as well as the instance type, which is completely optional, but it helps us drive it during the demo. You also have the option of specifying a minimum vCPU count and minimum storage size. That will affect your cluster size. Currently, we do have 24 vCPUs spread across 3 availability zones. So with the current minimum, ScyllaDB xCloud estimates it to 1 I4I2X large machine per zone or per AZ. What we'll do is instead of 8, which is the current number, we'll bump it up to 16, which with ScyllaDB should 24. Okay, so that's the total number, sorry. So instead of 24, let's go to 48. Sorry about that. And then we have the estimation of 2 instances per zone, exactly what we want to do as we scale the cluster horizontally. Instead of just doubling the cluster, let's just go ahead and triple it. And with a total of 72 vCPUs, it will bump to 3 instances per zone, 9 instances total, and help to scale out the cluster even more. So we will effectively triple the cluster size in a single shot. And as we save, ScyllaDB xCloud immediately starts to add those nodes and to adjust the cluster capacity following our newly specified workload pattern. And as we look in here on monitoring panels, currently this cluster is, as I said, composed of just 3 nodes with 21 vCPU shards, 24 total vCPUs using for interrupts, and a total of 104, 105K operations per second across this cluster. So after we kick it off the demo, let's go back to the presentation now. So now let's look at the test that we ran to reach 2 million operations per second on a small 3-node cluster, starting from a small 3-node cluster. So we started with just 3 nodes of i4i4x large. We ingested 2 terabytes of data using replication factor of 3, and then we initiated a workload that will continuously hit the cluster as we scaled. In Cassandra, we started with 56K ops per second, increasing incrementally as we finished scaling by order of 3 nodes, so 1 node per rack, and then we added additional capacity. While in Scylla, we started off at 200K ops per second with the same 3 nodes, keep that in mind, and waited for 3 more nodes to join, then bumped it up to 2 million operations per second. In Scylla, as mentioned, we only needed to add 3 nodes of i4i32x large, which are really powerful, large machines that you can find on AWS. In Cassandra, on the other hand, we added 69 nodes of i4i4x large, horizontally scaling the cluster, effectively adding 1 node at a time. And let's look at the scaling time for each operation in that regard. While scaling to those 2 million operations per second, ScyllaDB finished bootstrapping and was serving the full load at just 15 minutes after the start of the operation. While Cassandra took over 5 hours just to complete scaling horizontally, plus roughly 2 hours to clean up the data set on all those 72 nodes. While Cassandra took over those 5 hours, you can see that ScyllaDB is actually 26 times faster to scale from a small 3-node cluster to 2 million operations per second than Cassandra, following a roughly 2 terabytes data set. All done in ScyllaDB in a single operation, adding 3 nodes in parallel on one shot. And note that those are nodes of a different size. So while we started with just 3 4x large nodes, and then we added 32x large, ScyllaDB notices the difference in shard count and distributes tablets accordingly. So the full cluster performance is still retained at the shard level as data is streamed and tablets are streamed across those new nodes. And one would expect that scaling Cassandra cluster would be faster after some time, but in reality, after just a few rounds of operations, node add time became pretty much linear for Cassandra. Here we see the old net time starting from the 4th node, so the first one to scale the cluster, until the 72nd node. And around the 45th node being added, most of the operation took over just a little over 3 minutes to complete for every node. Even at this stage, where we transfer less than 300 gigabytes of data in each of those operations. And you might be asking yourself, why does that happen? So looking closer at the last node that joins the cluster, we see the breakdown of time between each stage of the node startup. So first, after systemctl start returns, the node spends 28 seconds initializing the Cassandra process, basically allocating memory. As the node is fairly large, it allocates roughly 32 gigabytes of heap memory before starting the process. After that, it takes over a minute for the node to contact the cluster and wait for gossip to settle, which is pretty standard, including those sleeps of roughly 30 seconds that it takes on some of the rounds. And last but not least, actual data transfer occurs at almost 2 minutes runtime. After transferring just less than 90 gigabytes of data, the node fully joins the cluster and is fully operational, allowing us to move to the next item. Whereas in ScyllaDB, the server process starts really fast and immediately joins the cluster empty. The tablet load balancer then notices the topology change and starts to distribute tablets according to the node capacity. As tablets finish streaming to the new nodes, client drivers are notified of the change, and then it starts to route requests according to the new node that owns that piece of data. This distributes data gradually to those new nodes, shifting the load from existing nodes. The process is actually continuous. So as the load balancer is always monitoring for imbalances in those tablet distributions, it is actively it's acting to evenly balance out the load across the cluster. So you might be asking yourself, what does all that mean in terms of cost? It means that if you have a throughput-oriented workload where you frequently require heavy data ingestion and your workload may be very spiky, ScyllaDB cuts off your ingestion times quite dramatically. The underlying infrastructure, features such as workload prioritization, can even allow you to consolidate multiple workloads under a single cluster, all while requiring much less infrastructure. This is really the case that Felipe mentioned, where in Cassandra, you would usually have two data centers, one for live operations and one for analytics in order to not interfere with live operation latencies, where in ScyllaDB, you can and should run those workloads across on the same cluster, the same data center, while leveraging workload prioritization to properly prioritize them across each other. If you happen to run a latency-sensitive workload, on the other hand, ScyllaDB will provide you very predictable latencies through zero pauses and even no those tail latency spikes. ScyllaDB is a much more efficient database overall. And even all the hardcore tuning that we did to Cassandra itself, we still didn't see latency being on a predictable scenario as it happens with ScyllaDB. All those numbers you saw are under extremely heavy tuning that the cluster underwent in order to run this benchmark. Latency-sensitive workloads also have lots of benefits from tablets, as our instant scaling makes it much easier for you to 2x, 3x, or even 10x your traffic. You just add nodes in parallel, single operation, and leave it all up for ScyllaDB to handle the rest of the ensemble. And finally, you might run a storage-dense workload with hundreds of terabytes or even petabytes of replicated data. You will for sure benefit from ScyllaDB's advanced compression for SSTables, which leverages dictionary to further compress your data set and reduce the overall storage cost. And if that's the latter one is your case, here's an exercise that we have for you. Logging into one of your Cassandra nodes or ask your DBA to do so, and then check how much free disk space you have on those machines. With ScyllaDB, we guarantee that you can reach your storage utilization up to 90% before you actually have to scale out your cluster due to disk shortage. Now let's touch upon a less obvious angle, observability. Databases are a really sensitive part of applications infrastructure. And obviously, observability is crucial to ensure that operational health and efficiency of the whole environment. Cassandra offers no centralized monitoring solution. While there are community-led efforts such as metrics collectors for Cassandra, it lacks support for the latest and greatest releases as well as some functionality in them. Each team usually comes up with their own set of dashboards, rule-based alerts, and we even see users that completely lack observability across their cluster because it's just so complex to do so. GMX is largely still required and pretty much a part of the ecosystem, and it adds up to the complexity of running and monitoring such a complex environment. Although newer versions of Cassandra may expose metrics in the Prometheus format directly, it lacks prominent features such as metrics for Java core, which are really needed when you're talking about optimizing your database for the best performance. As well as some monitoring as a service, such as Datadog, ActionOps, and whatnot. They also vary in coverage and depth. So it might be nice to get high-level metrics alongside your rest of your infrastructure signals, but it's usually hard for you to use those high-level metrics to really troubleshoot situations on a live scenario. Imagine your production is being affected by high tail latency. How do you go about solving them if you just rely on an external monitoring as a service solution? In ScyllaDB, through ScyllaDB monitoring stack, it offers a full out-of-the-box experience with a very rich monitoring set, composed of Prometheus with collection rules that calculate latency on the go and various alerts, Loki, which is a log processing, log aggregation service that also has log-based alerts, and Alert Manager, which has a set of alerts and customizable rules for different scenarios and needs. And of course, last but not least, Grafana with really powerful dashboards that spans all parts of the product. Those dashboards cover cluster metrics on different levels of granularity. So from cluster-wide view, or really bird's-eye view, looking at everything, to a per DC view, where you have metrics broken down into the data center level, as well as per instance metrics, which all of those is pretty familiar for Cassandra users and even other distributed databases. But Scylla really excels when it provides per shard metrics, which are metrics where you can see exactly how each shard in your whole cluster, doesn't matter how many nodes you have, how are they doing at any point in time. So let's say a single shard on your cluster is misbehaving, maybe through an imbalanced access pattern. ScyllaDB monitoring can actually help you map exactly which shards are those and help you direct your diagnose scenarios. And of course, we always recommend you staying up to date for the latest and greatest monitoring experience, and of course, to match your base ScyllaDB deployment. And with that, we ask you, how do you monitor your clusters? Are you leveraging existing monitoring stack? You might even share your favorite one on the chat, feel free to do so. Or are you leveraging third-party monitoring stacks such as Datadog, ActionOps, or maybe using cloud native if you're running directly on the cloud, if you're using AWS CloudWatch. I have users that simply use EC2 metrics to monitor your database, which is crazy. Or are you using a custom in-house monitoring system? And of course, there's also the option that you don't even actually monitor yet, but you know that you have to do so. And while you are looking at that, let's talk about operational simplicity. One of the major differences between Scylla and Cassandra. In Cassandra, there's a ton that you have to customize as you install and tune your system. There are system CTLs that you have to figure out how to set, how to persist, and you're responsible to do so across reboots. For disk, you have to understand what are your drives, what are their speeds, what are read-ahead settings to use, and even set rotational or non-rotational depending on the drive. And on JVM, don't even get me started. You have to pick the JVM version, you have to pick which GC option you use, as well as the whole tuning variety that GC option brings, as well as tuning heap size and other JVM metrics. And on top of all of that, there is still Cassandra.yaml with hundreds, maybe not hundreds, but at least many dozens of entries that you continue to tune your environment. As Felipe said, streaming throughput and many other caching or SSTable format tunables. While in ScyllaDB, on the other hand, it aims to do all of that for you. So it applies best practices all the way so you don't get lost in the details. We handle system CTLs, we handle disk setup, including in understanding the disk performance under different concurrent scenarios and using that information to drive our ScyllaDB internal scheduler. We handle hardware interrupts and we dedicate them to specific vCPUs to handle those interrupts so they won't interfere with shard processing. And of course, JVM is absent. So as it's built on C++, it runs closer to the hardware with no JVM dependency. And of course, ScyllaDB YAML is present, but it usually requires just simple or minimal changes, such as setting up the node IP, a cluster name, and some additional features that you might want to enable. And overall, it's a much simpler approach to configuration. Speaking of database management tasks, such as repairs and backups, ScyllaDB through Scylla Manager handles all of that for you, out of the box, from incremental backups to on-demand restores, as well as scheduler repairs with fine controls for intensity. In Cassandra, you have the popular community-driven options, such as Medusa for handling backups and restores, and Cassandra Reaper for scheduling those cluster-wide repairs. Whenever users are not using those, they're doing something that is even worse, which is just customizing, running bash scripts, or relying on cron, which is very unreliable. As well as the latest and greatest, hottest functionality, vector search. Both databases implement the vector data type. It's supported to build tables, and that will include vector characteristics. It allows that you use those vectors to run vector-specific approximate neighbor, nearest neighbors queries. Let's just refer that to ANNs, which find those similarities between embeddings. Both databases implement the CQL syntax pretty similarly and composed of select AN of and a vector and a limit, which vectors is the starting point for the similarity search. And this allows for the algorithm to use the database for the heavy lifting of that highly resource-intensive data processing task, which is great. But upon a closer inspection, each database implements it very differently under the hood. Vectors in Cassandra are implemented via storage attached indexes, or SAIs, and the JVector algorithm for AAN searches. This means that it shares the whole SSTable mechanisms and compaction lifecycles, tightly integrating that with the system. So as you leverage the implementation, it's also susceptible to the same issues. Data locality is a concern on large data sets with huge number of cross-partition queries, which might elevate latencies, as well as large partitions that can create data imbalance and affect compaction. So it also shares the same data path as regular queries, such as reads and writes, concurring for the same storage access, so really concurring to disk, and using the same chunk hash, if you're relying on that, to store page data from disk into memory. ScyllaDB is completely different implementation. Built as an external service, independent from the main database, it allows for maximum performance while keeping latency predictability within the database operations. So you don't want your database, your high ingestion time, or your ingestion pipeline to tank your live vector workload performance. It is an external service written in Rust, leveraging the usearch library, which is written in C++ itself, and has an amazing track record of performance of AAN queries. It is available in early access and fully managed on call. So if you're interested in exploring the vector search option with ScyllaDB, do contact us, and we'll engage on a hands-on process that will guide you through the whole exploration process. Now let's look a bit more closer to how ScyllaDB implemented vector and its architecture. So each AZ or availability zone has their own set of ScyllaDB nodes, as well as the vector search nodes. And those vector search nodes are engaged by ScyllaDB whenever an ANN query is required. So this is done via HTTP between ScyllaDB and the vector service. And ScyllaDB will feed into a CDC, which is used by the vector nodes to keep up to date with incoming writes on the base table. So the service reads from the external service, the vector service reads CDC data from Scylla through CQL, which is very efficient to do those efficient bulk reads to read from the CDC log tables. And the users, of course, interact with the database by writing data into the indexes table and by reading data back via the select with AAN filters, a very scalable architecture, as everything that Scylla does. And let's go back to our demo as we trigger the scaling. So let's just refresh the page here. And now we see that instead of just the initial 3 nodes, we now have 9 nodes listed. All of them are normal. Let's look at monitoring to see what's the current performance of the cluster. So we see that as the scaling finished, we jumped from roughly 100 k-ops per second to over 300 k-ops per second. Let's look at the detailed view and look at the instance level, where we see that in here, as the cluster was scaling, let me zoom into that. As those nodes were joining, tablets were being transferred to those nodes in real time. And as those tablets were transferred, the client drivers were notified and they reached to those new nodes with their writing operation. So it's really something that balances out across time. And then the workload kicks off with adding more operations as the cluster finished scaling. We're almost out of time here, so let me just quickly wrap it up. Benchmarks are really complicated and technical comparisons are even more so. ScyllaDB on our test excelled in stable latencies, while Cassandra saw frequent spikes caused by those GC pulses. We tested many different approaches aiming at a very fair testing, but it's impossible to test every combination. So if we missed anything, feel free to let us know. ScyllaDB outperformed Cassandra in every aspect: performance, scaling, costs, but also admin time. So if you want a sample of complexity, check out the process of upgrading Cassandra cluster, for example. ScyllaDB also offers tons of additional features, such as workload prioritization, the DynamoDB compatible API, via Alternator, as well as a really integrated, tightly integrated monitoring, no GC pauses, and whatnot. While both databases evolved on their own path, ScyllaDB focused on maintaining the high performance, scalability, and adding vector features, all the while helping users reduce and lower costs. Cassandra, on the other hand, is built for commodity, aiming at general purposes, NoSQL, general use cases with a broader latency tolerance. So if you have a higher latency tolerance, you might not even care about your database performance. We invite you to keep on learning through these resources, such as ScyllaDB X Cloud, really for fast, max efficiency, and lowering cost at cylladb.com/cloud. We also invite you to register for P99Conf and to register for ScyllaDB University Live, which is a really live learning event that is upcoming real recently. Felipe, do we have a minute? Do you want to answer any questions live?
I was just mentioning on chat that I found it fascinating when you showed like you basically 3x the cluster in less than 20 minutes. I think that it's very different really from how Cassandra works. And I think, yeah, I think what you mentioned about Cassandra being a database that was originally made for running on commodity hardware makes total sense, right? I mean, if we look back into the results we shared, it's definitely not bad performance at all. I mean, Cassandra 5 really can get you there in a 3-node cluster, over 100,000 operations per second, and under good latency. But yeah, I mean, ScyllaDB is often used by the extremes, right? That's typically when our people would start looking at us. We had lots of conversations on chat about the per partition rate limiting feature, which yes, it's a guardrail feature of ScyllaDB only, and we also allow sharding requests on concurrency level. And yeah, I mean, I think from those events which we are going to have, P99Conf will feature several talks from ScyllaDB, including more details about our vector search internals. So really, P99Conf is next week, folks. So if you haven't registered yet, please do register, because we'll have talks from Uber, from Netflix, from Meta, from Facebook, from several big companies out there, and from a variety of topics, right? Vector search, AI, machine learning, observability, and things like that. And we really hope to see you there. So all that said, Guy, I think that's it.
That's it. Thank you so much, audience. Thank you for your time, and I hope we have added with more information for you. Feel free to reach out to us and share your comments and your thoughts. Thank you again.
Thanks, guys.